Now we're going to look at a halogenation of alkenes. And instead of adding H and a halogen across the double bond, we're going to add a halogen and a halogen across the double bond. This works well for Cl2, Br2, and I2. Here's the basic process. We take an alkene. I'm going to write it with all the atoms to start. And say we add Cl2 to this. And sometimes you'll see something written under this, CH2Cl2. This, if you see that, it's dichloromethane. It has nothing to do with the Cl2 reagent, despite the fact that it does contain chlorines. This is just a solvent. When we're doing reactions, we really don't need to think too much about how the solvent gets involved. Just know that it's a solvent that helps dissolve your starting materials. When the reaction occurs, we're going to add Cl and Cl across this double bond. So just like with adding an acid, you go from the double bond to the single bond. All right, we don't add or lose hydrogens or carbons, but now each carbon will have a Cl attached. Let's now look at the mechanism to see how this is happening. Here's our alkene and Cl2, and there's actually a bit going on in this first step. We use the pi bond in the alkene, and let me actually I'm going to make this pi bond green so we can keep track of it. That attacks one of the chlorines. The other chlorine is lost as a leaving group. And then at the same time, instead of forming a carbocation, one of the lone pairs on this first chlorine comes and bonds with the carbon of the double bond. So if we track the electron flow here, I end up with the green pi bond forming one bond to the Cl, the pink lone pair from the Cl forming the other bond to the carbon. This chlorine still has two lone pairs on it. And then I end up with Cl minus that has now four lone pairs. We have this chlorine with an unusual number of bonds. If you calculate its formal charge, you should find that it has a positive formal charge. This species here is known as a chloronium ion. It might be kind of tempting to think about this more like adding the acid, where you just start with the double bond, add it to the chlorine, and lose the other chlorine as a leaving group to get this type of intermediate. The carbocation. And then thinking about that, going to here, using one of the lone pairs. This does not form. Why is that? Well, when we use a hydrogen in the first step, the hydrogen doesn't have any lone pairs, so you're basically stuck with adding the hydrogen and getting the carbocation. But when you use something with a lone pair like the chlorine, rather than forming an unstable carbocation, it can donate its lone pair to form something that's not quite as bad, because carbocations are very unstable. So this chloronium ion is lower in energy than this carbocation that could have formed. So this is a preferred intermediate. From here, now we want to end up with our neutral product, and the Cl- is going to act as a nucleophile, and it can add to either one of these carbons. So let's just add it to the top carbon. If I add it there, it's going to break this bond and put a lone pair on the chlorine. We still have the chlorine attached by the green bond. And then the new Cl is also attached. And that's how we end up with the two halogens added across the double bond. I want to talk about a common mistake that people make when drawing this mechanism, and they often think, well, why shouldn't we take this Cl- nucleophile and attack the positively charged Cl? After all, negative and a positive, shouldn't that be an electrophile that the nucleophile is attacking? Well, no. The problem with this, if you draw the outcome of this reaction, what we're doing is giving yet another bond to this Cl, and if you count the electrons around this chlorine now has 10 electrons. Up here, it has an octet. It doesn't want 2 more electrons. So that's why we don't attack the chlorine directly. What's the better thing to do is attack the neighboring carbon like this, and that'll put a lone pair on the chlorine to deal with the charge such that it's now neutral. So in a single step, now we have a neutral structure, everything has its octet, everything's in good shape. Now we're going to take a look at the stereochemistry of halogenation. And one thing to keep in mind as we do this, in these halogenations, the halogens always add trans to one another, so they'll end up on opposite sides. Let's take a look at an animation of this. Here we're going to take cyclopentene and react it with Cl2, and what we find in the products is that you'll have Cl added, but one will be out, the other will be back, and then in a second product, it can do it in the opposite direction. So this Cl's out, and this Cl is back. And these two are enantiomers. Let's look at this a little bit more mechanistically. I'm going to redraw my starting material. This time I'm going to draw the hydrogens in just so we can keep track of them. And when this reacts with Cl2, we'll draw in our arrows, start at the double bond, attack a chlorine, lose the other as a leaving group, and then a lone pair from the first chlorine comes in and bonds to one of the carbons. Now the thing is, this double bond is planar. So this Cl can add from the front or the back. And let's draw both outcomes. If it adds from the front, the chloronium ion will be on wedges. Like that. And then that means the hydrogen will be back as dashes. If it adds from the back, now the chloronium ion will be on dashes, and the hydrogen will be wedges. Now in this particular example, there's a plane of symmetry that runs through this molecule, and that means these two are identical. That's not always going to be the case. Sometimes you'll get the two chloronium ions that can be enantiomers or diastereomers, but in this case they're identical, so you really only need to consider one as far as how the rest of the products result. So now let's take this first one and we'll react this with a chloride anion. And I'll do it in a different color just to help us keep track of it. One thing to keep in mind is that when you're adding a nucleophile to an electrophile, we have the leaving group coming off of that electrophile. The nucleophile always adds opposite to the leaving group. The reason behind that's a little bit beyond the scope of this course, but it has to do with the way the orbitals are aligned. That means if my leaving group, the chloronium ion, is out, this Cl- will attack from the back. And as it does, it comes in from the very, very back. So it comes in, displaces the leaving group bond, but it comes in from even further behind than this hydrogen. So as it adds from the back, this hydrogen comes out to the front. So now in our product, we have this Cl and hydrogen, and then our new Cl that added came in opposite that other Cl. So this one will be back, and then the hydrogen will now be on a wedge because it got pushed to the front. Now that chloride ion can attack the other carbon of the chloronium ion. If it does, we'll add there and break that open. When we draw the product for that, that means the new Cl will be on this bottom carbon, but it will still be back opposite the leaving group. So there's a Cl. The hydrogen will be on a wedge. Here's our Cl from the chloronium ion. And this hydrogen's a dash. So here we get a pair of enantiomers. If you were to do the reaction with this other species, because it's identical to this one, you end up with the same two products. Let's take a look at this problem here where we have a chiral starting material and we're reacting with Br2. Again, the reaction is taking place at this double bond. So you don't want to mess with your original chiral center. That's going to stay the same in all of the products. The Br2 can add from the front side and the back side of this double bond to give us two bromonium ion intermediates. So let's look at those. Okay, so in the first one, we have the bromonium ion added from the front, and again I put both on wedges. I know generally I say don't put a wedge in the small angle of the bond here, but there's no way to avoid that when drawing this bromonium ion. And then when it comes in from the back side, now we have dashes to the bromonium ion. With this, we have the option now of adding our nucleophile, the Br-, to carbon A or carbon B, carbon C or carbon D. And bear in mind, now these two intermediates are different. In fact, they're diastereomers. So we need to consider the reaction at both of these. So when you're doing this type of problem, regardless of what starting material you get, it's always a good idea to draw both bromonium ion stereoisomers And now we're going to consider what products we get if we react each with Br-. So let's start with this top one. And if we react this bromide at carbon A, it's going to come in from the back. So we'll end up with the bromide on a dash. And that's what we have here. So I drew it in blue. This new bromide that I added was at carbon A, and it ended up as a dash. The second one stays on the wedge. Now let's look at adding the bromide to carbon B. If we add it to B, it'll add and open that up, and you get a second product, but now the new Br is added to this position, and again it's back trans to the stereochemistry of the bromonium ion. Now let's do the same thing with our other bromonium ion stereoisomer and see what happens if we add the bromide to carbon C. So if we do that, we're going to add it opposite this leaving group, so it'll end up on a wedge. And we get this product. And then finally, let's look at adding it to carbon D. In D, the bromide adds from the front to this bromonium ion, opens that up, so the new one ends up as a wedge. Now analyze all of your products. And don't compare them based on the color coding, because a bromine is a bromine regardless of whether it's in blue or black. But now if we look at these, hopefully you can see that products B and C are identical compounds. We have a dashed phenyl, wedged Br, dash Br, dash Br. So those two are identical. Then if you look at A and D, you can see that A and D have the same stereochemistry at each of the 3 chiral centers, so those are identical. So in the end, what we really end up with is just 2 different products. But what I encourage you to do anytime you're working one of these problems is to go through and draw all 4 possible products and then compare them. Sometimes they may be the same, sometimes they may all 4 be different. A couple of other things to take note of just in general. When you're doing halogen addition, there's no carbocation intermediate in the mechanism. That means there's no Markovnikov's rule or Markovnikov selectivity. You also don't have to worry about carbocation rearrangement.